To wrap up the course, I want to, um, what we're going to do is we're going to take a really big step back with spectral theory and its applications, right? This is very focused on a certain subset of algebra, right? All of this matrix theory is really algebra that's going on, right? This we call it linear algebra or matrix theory. Let's take a huge step back and think about like a bigger setting or a more abstract setting for a second here. And to kind of get us in that mindset, I want to start by talking about the dichotomy of geometry and algebra here. So we know there is a very, very in-depth and intertwined relationship between geometry and algebra. And it almost does it a disservice to call it a dichotomy because a lot of the notions in geometry can be explained via algebra, vice versa, right? So it's like a lot of these, you think of, math as this some nebulous subject of knowledge here, and then sometimes you always think about like, oh, okay, well, here I have geometry, here I have algebra, here I have calculus, over here, if you've ever heard of like topology, it's basically abstract geometry, which is actually what my research is in, topology, and you could, even within algebra, you could break, you could start to make other subsets here. But these are far from disjoint, right? The techniques used and the concepts from each kind of sub genre of math, if you will, a lot of the times it's describing the same phenomenon, right? For example, when we looked at vector addition, we had two vectors v and w. Well, we understood the geometric interpretation of the sum of two vectors, right? We had v, w, and then v plus w was that resultant vector there, right? But we also had an algebraic understanding of, if you wrote these vectors component-wise, like v1, v2, and w was w1, w2, then we understood what v plus w was algebraically, right? Here, this is algebraically because we're using operations and equality, properties of adding real numbers, things like this, right? It's very algebraic. We understood vector addition in this way, like v1 plus w1, v2 plus w2. And so really it's kind of two sides of the same coin here with geometry and algebra. To motivate the discussion of vector spaces in general, let's start with looking at a vector space that we're already very familiar with, right? Calculus 3 is basically the study of the vector space V equals R3, right? Because you do so much vector algebra and calculus in three-dimensional space, right? We were setting up double and triple integrals. In R3, we had vector line integrals, surface integrals, all this. So maybe I should say like R2 or R3, or even R4, depending on, right? Because the graph of, well, if you're integrating, say, a function of three variables, then the graph of that function is in R4, but whatever, on a tangent. So when we are looking at the properties of, so let's say, not to make this R3, but let's say this is Rn here, right? We have all these properties that vector addition satisfies, right? We know for any vectors, there was this whole list, right? It's the sum of two vectors is a vector. You can scale a vector. You can, like, there's a notion of a zero vector or an additive identity. There's the notion of one, right? The real number one, which is a multiplicative or a scalar multiplicative identity, all of this stuff. And we apply that to vectors in Rn, right? And then what we were studying before we started spectral theory is we were studying basically linear transformations in the vector space Rn, right? We were understanding how vectors are transformed as you rotate or reflect or whatever, right? And we can do that because vectors obey such nice properties, right? The properties of vector addition behaves quote unquote as you would like it to, right? It behaves very nicely. Scalar multiplication behaves very nicely. It allows you to do all of these things and apply this to develop theory of like linear transformations. And, then you can get into things like spectral theory, which has a spectrum of applications. But what is so special about Rn? What is so special about this vector, right? Is that the only thing that could ever obey some certain list of properties? And that's the question that we're going to explore here. So instead of saying, here's vectors, and then it turns out they satisfy all these properties, we're going to go the other way. We're going to say, we're going to state all of these properties as axioms, and then we'll see what other objects, collections, sets, what other objects behave as vectors do, right? And so really, there is nothing special about the behavior of a vector behaving that way because it is a vector, right? It behaves that way because the properties of its addition and scalar multiplication make it a vector space, right? And so to kind of recap here, instead of, saying we know vectors and their operations, vector addition and scalar multiplication, let's say we know that the operations obey many properties, or let's just say certain. But now what we want to do is we want to take that list of properties and see what other sets behave that way. And it doesn't have to be geometric necessarily, right? Vectors are extremely geometric. They're a very intuitive and easy example of a vector space. Not an easy example, but easy to picture and grasp example, right? It's very hard to, it's much easier to understand something if you can also picture it, right? But there are certain sets that behave like vectors, even though they may not necessarily have an extremely geometric meaning. The examples that we will explore, there is geometry still going on here, but it's certainly not a collection of vectors anymore, right? So let's define what a vector space is in general. We'll start with a definition. So before the definition, let's say V is a set of, and we'll call them vectors because, we call these vector spaces, right? In general, if you would like to take a more abstract approach, let's just let this be a set of objects. Right? We'll think of it as vectors, but vectors. So this is a set of, points, vectors, things of this nature, right? And we'll go through examples of different types of objects, but for now, let's just say, let's just call them vectors. By plus, we will denote addition operation defined on all elements of the set V. And then we'll denote scalar multiplication. So this is the scalar multiplication operation defined for all scalars A and R on elements of V, right? And so we're used to this with, say the sum of two vectors or the sum of two matrices or, the sum of two numbers, right? To emphasize the abstractness here, right? When we say an addition operation, notice it's not the addition operation. It's an addition operation, right? That means addition by nature can be defined, or by its definition, can be defined a priori arbitrarily, right? I could say, well, I'll get there. Just to show an example, if you take 5 plus 3, and that's 8, great. Well, what about then when you add two vectors? You take 5, 5 plus 3, 3, and you get 8, 8. You're still adding the numbers 5 and 3 to get 8, but as an operation, addition here is behaving differently than it is here, right? Because the inputs are different. I mean, you could argue that it's the same thing, right? Because this is a one-dimensional vector, right? Or just like a 1-by-1 matrix. And so you could think of adding scalars as just matrix addition. But you can see that sums and products need not be defined as intuitively as we would think, or as we've always worked with addition. Same for scalar multiplication. We won't see any super wild examples, but just so you can kind of get the idea of how abstract a lot of this can be. And we won't address this either, but you can also define, right? We're looking at vector spaces, and like our scalars are real numbers. And we're going to be using real numbers as like coefficients or entries of a matrix or things like this. But this also need not be the real numbers. There is a notion of a field. A field is basically a collection of, or a set that behaves as the real numbers do, right? So for example, the complex numbers are a field. The real numbers are a field. You have notions of like addition, subtraction, multiplication, division, right, et cetera, et cetera. And so you can define vector spaces over an arbitrary field, but we won't get into that. We'll stick to just the field of real numbers here. But I do just want to kind of, again, I'm trying to emphasize and motivate the abstractness that's going on here. So what is then a vector space? Let's give a definition. So I'll write this as, so let's say the triple V plus multiplication is a vector space if the operations plus and multiplication satisfy their, or let's say the respective axioms. Okay, so what I'll do now is I'll list axioms of like properties for addition and scalar multiplication, and then this triple here, if addition satisfies all of the addition axioms, if scalar multiplication satisfies all of the multiplication axioms, then we say that this triple is a vector space, right? And really we just think about what I'll do is, really you're just thinking about the set as being a space, right? But it is important to note that that set on its own is not what makes it a vector space. It's that set and the existence of an addition and multiplication operation that make it into a space, right? So now let's look at the addition axioms, right? Okay, so what are axioms, right? Axioms are kind of like laws. You can think about them as things that must be followed or satisfied for something to be upheld, right? So we must require for an addition operation on a set for it to be to turn V into a vector space, we need that the addition satisfies the following conditions here. First, we need that V is closed under addition. What does that mean? That means for every pair, and so let's just let V and W be elements of the vector space V. Hopefully my lowercase and uppercase, you can differentiate here. This means for every pair of elements, this implies that V plus W is also in the vector space, right? So maybe let's get rid of the for all. Let's just say if V and W are in the vector space, then the sum is also, right? That's the first axiom. The second is commutativity, which states, you can switch the order. Whoops, I'm not doing the little. So V plus W would be W plus V. We have that it satisfies associativity, right? These are all things that you're probably very familiar with because these are the properties that vector addition, as we know it, satisfies, right? We have associativity, so that means if you have three elements, say V plus W, but first we do V plus W and then plus some third element Z, then so I don't have to write this every single time. Let's just write V, W, Z. These are elements of the vector space, right? So that way it's just understood. You can take V plus W first and then add Z, or you can take V plus first doing W plus Z. We need that there exists an identity. So there exists an additive identity, i.e. there exists zero. We denote it as zero, right? We need not denote it as zero per se. And you'll see in some examples we won't, but there exists zero element such that V plus 0 is equal to V for all V and V, right? So this is your additive identity. We also require that there exists an additive inverse. And that means for all V in V, there exists W, which we'll think of as negative V, right? Because that's the additive inverse here. For all elements V, there exists this element W or negative V such that V plus W equals 0. And really, we're just thinking about this as negative V, right? So if you can define an operation on a given set that satisfies all of these properties, then that is an operation that can be that can turn V into a vector space here, right? But not only do we need this, we also have to be able to find a scalar multiplication operation here. So let's define the axioms for scalar multiplication. So for scalar multiplication, first we need Sorry, I'm lost here. We need that V, oh, whoops. So scalar multiplication axioms. We need that V is closed under scalar multiplication, i.e., for all scalars A and R, let's use K. I like K for a scalar. For all K and R, if V is an element of V, that implies that KV is an element of the vector space V, right? That's what it means to be closed under scalar multiplication. Sorry for the messy handwriting here. We also have element distribution or element distributivity. Excuse me. We have the distributive property for elements of the vector space. So I'll just write element distribution, which means if you take a scalar A times V plus W, that's the same as AV plus AW. We also have like the scalar multiplication distributive property, which means if you took like A plus B times V, that's AV plus BV. And I guess I gave up on K right away. So let's just go back to A. And we also need the notion of scalar associativity, i.e., if you have like, let's say you're taking A and then multiplying that by BV, well, that should be equal to first AB times V, right? And then lastly, we need the existence of an identity, i.e., there exists an element 1 such that 1 times V equals V for all V in V, right? So there's kind of a lot here to check with these operations to prove that something is a vector space, but that's exactly how you prove something is a vector space, or that a given set is a vector space, right? What you have to do is you have to, on a given set V, you have to see which operation or how the addition and the scalar multiplication operations are defined. And then for each operation, so for the addition operation, you have to prove axioms 1, 2, 3, 4, 5, right? You have to prove all of those. And then for scalar multiplication, you have to prove all 5 axioms. And so what we'll do from here is, now that we've kind of introduced vector spaces and how it's a generalization of the arithmetic and algebra we've been doing in n-dimensional Euclidean space, what I want to do in the next video is dedicate it purely to examples, right? Because although it's good to understand abstract things, right? It's very important to study abstract things. It does help to see explicit examples, right? And so that's what we'll be doing in the next videos. We'll be looking through a bunch of new examples of vector spaces besides just Rn.